let's keep adding to our knowledge of the 4 skills in this unit. So comparing properties of reciprocal functions, let's do this algebraically, so without a graph. So where will g is the reciprocal of f, where will g have a vertical asymptote? This will be when f equals 0. So when is x squared plus 2x equal to 0? To determine that, we'll have to common factor out an x. So we'll see that it equals 0 when x is minus 2 or 0. So then g of x has VAs at x equals minus 2 and 0. F and g will intersect when f is 1 or negative 1. So f will equal 1 when x squared and 2x is 1, or when x squared and 2x minus 1 is equal to 0. There are no numbers that multiply to minus 1 and add to 2, so I will have to work this out using the quadratic formula. X will equal negative 2 plus or minus 2 squared, so that's 4 minus 4 times minus 1, so that's 4 plus 4, so and over 2a. So I have minus 2 plus or minus root 8 over 2. Simplifying that, the root of 8 is the root of 4 times the root of 2, so that's 2 root 2 over 2. So this equals minus 1 plus or minus root 2. Okay, so f at x equals 1 when x is 1 plus or minus root 2. And f at x, so x squared plus 2x equals minus 1 when x squared and 2x plus 1 is 0. This is nice. This is just when x plus 1 squared is 0. So this is just at x equals minus 1. So f and g will intersect at 3 points. So they intersect, first of all, at minus 1 plus root 2, and the y value is 1. Minus 1 plus root 2 has a y value, minus root 2 has also a y value of 1. And this other point, x is minus 1 when y is minus 1. So we've got those 3 points of intersection. So g of x will have positive intervals when f at x has positive intervals. So when is x squared plus 2x greater than 0? This is a polynomial inequality which is easily solved if we can factor it and therefore sketch it. So we've got negative 2 and 0 opening up. So we can see that both f and g are positive. So f and g are greater than equal to 0 when x is negative infinity to negative 2 and 0 on. So g of x will be increasing when f at x is decreasing. So doing this sketch again, we have negative 2, 0. Okay, so our function increases until the vertex. The vertex will occur halfway between the zeros, so it occurs when x is negative 1. So f at x is decreasing from negative infinity to negative 1. Therefore, g of x is increasing and it's not quite the opposite because we have to take out the VA. Negative infinity to negative 2 and negative 2 to negative 1. Okay, so using those properties algebraically is a slight variation on what we've been talking about for pairs of reciprocal functions. So now with rational functions, we are going to look a bit more deeply into their end behaviors. So we've talked about horizontal asymptotes. There are other functions that don't have a horizontal asymptote. They actually have something that's called an oblique or a slant asymptote. This type of asymptote is going to occur when the degree of the numerator is exactly 1 greater than the degree of the denominator. So for this function, we have x squared over x. The degree is 1 greater. And so our asymptote, you'll see the dotted line here, is actually a line with slope, not just a horizontal line. But we get this end behavior by doing the same thing we've been always doing, which is dividing the numerator by the denominator. We're just going to actually complete this division. So using long division, I'm going to put 0x in, so I have all the terms represented. I'm going to have x squared minus 3 divided by x plus 2. So x squared divided by x is x. X times x is x squared, and x times 2 is 2x. Then I subtract, I get minus 2x. I bring down the minus 3. Minus 2x divided by x is minus 2. Then I multiply, I get minus 2x minus 4. And so I have a remainder of 1. So we've got a division statement that we can write here. Division statement. Okay, and we have that x squared minus 3 over x plus 2 is equal to x minus 2 plus the remainder, which is a fraction of the divisor. So now think as x is getting really large, so that's our approaching plus or minus infinity, this fractional part approaches 0. So the function acts more and more like the quotient, which is x minus 2. That becomes the equation of the oblique asymptote. So our oblique asymptote is y equals x minus 2. So note that x minus 2 is a line with positive slope going like this. Its end behaviors are as x approaches infinity, so does y. And as x approaches negative infinity, so does y. And note that these are the end behaviors of the function. Here our x's are approaching infinity, and so are the y's. X's are approaching negative infinity, and so are the y's. Okay, so next example. First of all, is there an oblique asymptote? Yes, our numerator is degree 2, our denominator is degree 1. So we have 1 degree greater. Therefore, there will be an oblique asymptote. So to find that oblique asymptote, x squared plus 0x minus 4 is going to be divided by x minus 3. So I'll get x, and I get x squared minus 3x. When I subtract, I get 3x. I bring down the minus 4. 3x divided by x is plus 3. Then I'll get 3x minus 9. And honestly, this remainder doesn't matter. It's 5. This part we can just ignore. If you don't even finish that part of the division, honestly, I'm okay with it. So now we're going to sketch the graph using our 4 properties. So we want to know our x-intercepts. They are when x is plus or minus 2, coming from this numerator. Our y-intercept is when x equals 0, so I have negative 4 over negative 3, or 4/3. Our VA occurs when the denominator equals 0, so when x is 3. And then our end behaviors this time are an oblique asymptote, and that is the equation y equals x plus 3. So let's start by drawing a VA at 3 using my ruler. And my OA is at x plus 3, so up 3 and over 1, up 1. Okay, using my ruler. Whoops, not forgetting to put the pen down. Okay. I have x-intercepts at plus 2 and minus 2, and a y-intercept at 4/3. So what is happening is between this asymptote, I'm going like this. On the right side, I can't be coming up from below because that would create another x-intercept. So I'm just going to have part of the function in there, so heading off towards negative infinity. and not crossing the vertical asymptote. Okay, so next thing to be aware of is that type of asymptote. So solving rational equations algebraically, let's perform our method of getting rid of the denominator. So first of all, noting that x can't be equal to plus or minus 2. And here, when we've got fraction equals fraction, we can just multiply them, cross multiply them, right? And then we get x squared minus 2x is 5x squared minus 20. I will move everything over to the right side, so I get 4x squared and 2x minus 2 is 0. I can divide everything by 2, and I'm going to switch sides while I'm at it. So I have 2x squared plus x minus 1 is 0. Minus 10, sorry, because that was a 20. This I think I can factor as 2x and x. And if I do 2x times 2, and then I add 5x, that makes 1. So this makes minus 4x plus 5x is 1. 5 times minus 2 is 10. So I get the values of negative 5 over 2 and 2. Okay, except 2 is one of our restricted values. This one is not restricted. Okay, so there's only one solution, and it's that x equals negative 5 over 2. So this is the importance of solve and check. Okay, so now solving this one algebraically, we can't just cross multiply because x plus 1 and x minus 3 are sometimes negative, and multiplying by something that's negative would change our sign. So instead, bring it over and make everything equal to 0. One side equal to 0. Then I want a common denominator of x plus 1 times x minus 3. X plus 3 needs to be multiplied by the other denominator, which is x minus 3. And x minus 2, so in brackets because of the negative, needs to be multiplied by x plus 1. Well, it's also in brackets just because there is multiplication happening. Okay, and then, this is x plus 3 times x minus 3, so that makes x squared minus 9. This makes x squared minus x minus 2. Everything's being subtracted, however. X squared minus x squared is nothing. Here I have minus minus x, which is positive, and minus 9 minus negative 2, well, so that makes x minus 7. Then I have x plus 1, x minus 3, and when is all of this greater than or equal to 0? Do you want to try sketching it? We could try that. So it's got a 0 at x equals 7. It has a y-intercept. I'm using this one. And plugging in 0 for x, I get negative 7 over negative 3, so a y-intercept at 7/3. There are VAs at minus 1 and 3 from the denominator. And the HA is, we've got an x divided by an x squared. So that's going to trend towards 0. Okay, so my VA at negative 1 and 3. HA at 0. A 0 over at 7. And a y-intercept at 7/3. Okay, so this one's looking rather strange. I'm going to definitely come in like this. Over here, I need to be, I'll have to test something. So like at negative 2, that will make negative 9 over negative 1 over negative 5. So that becomes negative. And here what's going to happen is I'm going to, at 4, that makes negative 3 over 5 times 1. So this is a negative number here. So I think what happens is I come through, I go through that 0, but then I come down towards the horizontal asymptote. You know what, I'm regretting, I think a table would have been easier. So, however, when is this negative? It's or equal to 0. Oh, no, I'm doing greater than. Yeah, I'm doing greater than or equal to 0. So that's from negative 1 until 3. And again, it becomes positive at the 7, but it equals 0 at the 7 up to infinity. Okay, so note that the restrictions are always round, but x equals 7 is the 0, and that's a square bracket. Okay, so that gives us a little bit more detail about each of the 4 things, and I hope that you are enjoying learning a little bit more about all of this stuff.